as a stepping stone on the way to understanding derivatives, differential calculus very well. We are going to start with limits. As I often do, I'm going to explain what a concept is by working you through an example. So limits are trivially easy to calculate for a continuous function. So for example, this function here, we actually already saw this in our first hands-on code demo, the only code demo we've had so far. So this is the function 2x squared plus 2x plus 2. So this is a completely continuous function. At any given point, there's no stoppage in the relationship between x and y. And so we could pick any point on this 2x squared plus 2x plus 2 curve. So let's say arbitrarily, let's say at the point 5, if we want to calculate what is the limit as x approaches 5, well, as I've already now mentioned, with a continuous function like this, it's trivially easy to calculate it. So we use this notation here to say what is the limit as x approaches 5. So limit, and then as x, and we've got an arrow towards 5 here, and then you put in brackets the equation that we are finding the limit in. So in a continuous function like this, we can just drop in 5 for x. So x squared becomes 5 squared, 2x becomes 2 times 5, 5 squared plus 2 times 5 plus 2. All right, so 5 squared is 25, 2 times 5 is 10, 2 is 2. And then we add them all up, 25 plus 10 plus 2 is 37. So the limit as x approaches 5 in the expression 2x squared plus 2x plus 2 is equal to 37. So all this means is that at this point here, where x is equal to 5, y is equal to 37. Straightforward. However, some functions are not continuous. So consider this function here, x squared minus 1 divided by x1. So this function produces a curve that looks like this blue line here, but critically, this is a discontinuous function. So at this point here, where x is equal to 1, there is nothing to compute here. So this function, though it appears to be continuous, it skips an infinitesimally small point at x equals 1. So we can calculate values that get very close to 1, down from higher values of x, or we can calculate numbers that get very close to x equals 1 from the bottom, so we can increase x towards 1 here, but then we can never calculate at x equals 1. And the reason for that is because you can't divide by 0. So this discontinuity is caused by at the point where x is equal to 1, then in the denominator of this fraction, 1 minus 1 is equal to 0, but dividing by 0 is impossible, and therefore the value of y at precisely 1 cannot be calculated by substituting 1 in for x in this equation. Despite that, we can calculate the limit as x approaches 1. So I've alluded to this already. So we can get very, very close to x equals 1 from the bottom, or very, very close to x equals 1 from the top. And just by looking at this graph, it's pretty clear that y is going to be equal to or approximately equal to 2 at that point as we approach 1. So that's what a limit is. So limits allow us to calculate what y is as we approach this point that we cannot calculate explicitly. Let's jump to a hands-on code demo to look at this more closely. Returning to our subject 3, which is on Calculus 1 notebook, we now have in this next section here in Colab, it collapses sections of code to reduce memory footprint. So you can click on this triangle here to open up the limits section that we'll tackle now. This first cell of code exists to create the plot that we looked at for an example from the slides. So it just creates this plot here. If you'd like to play around with that on your own, it's using the y equals x squared plus 2x plus 2 function that we already had in memory from the earlier hands-on code demo. And I'm plotting out the line itself with this plot call. And then other elements of the plot, we've got the x and y values of 0 represented in light gray. We've got our limits. So I just picked limits of -5 up to 10 for the x-axis and -10 up to 80 for the y-axis. That looked nice for what I'm trying to show here. And then as we calculated in the equation on the slides, at x equals 5, y is equal to 37. And so I just plotted this kind of crosshair with purple hatched lines to indicate that point. All right, moving on to our example where we can't simply plug in 1. So remember, 1 minus 1 gives us 0. So this is the function that we were most recently looking at in the slides. So if we'd like to explore with the hands-on code demo how we can identify the value as x approaches 1, well, we can do that kind of empirically here with code. So I'm going to start off by defining a function called myFunction, which simply is this function here. So x squared minus 1, divided by x minus 1. And to prove the point, this should be obvious, but if we try to do 1 minus 1, so if we try to calculate exactly what y is equal to at x equals 1, we will get a division by 0 error, because 1 minus 1 is 0. So just leave that commented for now. However, even though we can't calculate at exactly x equals 1, we can get very, very close to 1, infinitely close to 1 in the spirit of calculus of the infinitesimals. So let's say at 0.9, I mean, that's pretty close to 1. What is y equal to at 0.9? Well, it's equal to 1.9. Let's get even closer to 1, so 0.999. Yeah, well, we get even closer to what y is equal to as x approaches 1. So now we can see that it's going to be 2. 2 is the value that we're approaching of y as x gets very, very close to 1. And we can do the same thing from the other side. So this is from the bottom approaching 1, but we can also approach the limit from the top. So 1.1 is pretty close to 1 from the top. That gives us a value of 2.1, kind of close to 2. But as we get really close to 1, 1.001 from the top, we can see that we are approaching 2. So hopefully this is starting to make sense of what this limit idea is. And we can even plot all of this out. Luckily, because one of the values in x isn't exactly 1, we are able to compute the y curve for all of the 1,000 elements in our x vector. And we can create a plot similar to the plot that we had for our continuous function here. Now for our non-continuous function, this is what we had on the slides earlier, so I'm using a crosshair again to indicate this point. So even though we can't calculate what y is equal to at x equals 1 exactly, by using limits, we can determine what y is approaching as x approaches that limit of x equals 1. Right, so this is kind of this empirical way. I mean, you could do this with pencil and paper or even with a code notebook. We can get closer and closer. We can approach 1 kind of manually and ascertain for ourselves, okay, this looks like, the answer is 2. But instead of relying on empirically playing around with numbers and getting closer and closer to that x equals 1 limit, we can use algebra instead.